Alright, so here begins lecture 17, which is on continuity. So here's the definition. Let D be a non-empty subset of the reals and f a function. The function is said to be continuous at x0 in the domain. If for any real number epsilon positive greater than 0, there exists a delta greater than 0, such that if x is in the domain and within delta units of x0, then f of x minus f of x0 is less than epsilon. He says if f is continuous at every point in D, then we say f is continuous on D, or we just say it's continuous if there's no confusion, right? If the function is continuous on its domain, we just say it's a continuous function, right? But otherwise, you could pick a subset of the domain and talk about the function being continuous on a subset of the domain just the same, right? And so graphically, you can kind of look at this in terms of there's like an epsilon band, right? So like here's f of x plus epsilon naught. F of x naught plus epsilon's like up here, right? F of x naught minus epsilon's down there, right? So, and f of x naught, of course, is right in the middle. And so what's going on here? So we're going plus or minus epsilon. So this distance here is 2 epsilon, right? And the point here is if you're given such an epsilon greater than 0 for a continuous function, and you can pick, and so here's x naught right here, right? You can pick a delta greater than 0 such that the plus or minus delta band, right? Here's x minus delta right here, x naught minus delta, and here's x naught plus delta over here, right? And so this is a window, between these lines is 2 delta, right? So basically, the point is if the input is between plus or minus delta of x naught, then the output has to be within plus or minus epsilon of f of x naught, right? And that's just an inequality way of saying if you zoom in on the graph of the function, right, you can fit the graph of the function within an appropriately sized viewing box. See, the box is bigger than the, let's see if I can foolishly graph the box. I guess I'll use yellow for lack of imagination. So the box would be something like this, right? Like that. So this definition, what it's essentially saying is that if the function's continuous, you can't jump at that point, right? I mean, that's what we're trying to capture, is that the points in the graph are adherent to one another close by. So I decided to add an example here. So here's an example. Let f of x equal x squared plus bx plus c. I wanted to do it for arbitrary b and c for fun. And the domain is all reals, right? My claim is that f is continuous at x equals to x naught, and that's actually an arbitrary point, right? So if I can make this argument work, then we'll have shown that f is continuous on the reals. And of course it is, right? I mean, this is a quadratic, right? So the graph is a parabola. There's no jumps in a parabola, right? Anyway, so here's the scratch work. So we get to control x minus x naught being less than delta. We need to, whatever our choice of delta to be, to force f of x minus f of x naught to be less than epsilon, right? So what we're facing then, when you work it out, is this minus that, which works out to this. Of course, the c's cancel, right? The c's cancel, and what else can we say? The c's cancel. Then you can, group the stuff with b together like that. You can factor x minus x naught out of both of these, and you're left with x plus x naught and b times x minus x naught, which means that you can, break it up by properties of absolute value to the product of x minus x naught with this thing. So essentially, we need to get this under control with our choice of delta. So I explained below that we can bound this by a number m. I'll explain what that is in just a second here. But I mean, like once I get to this, I'm like, okay, well, I need to control that somehow. So the way to do it, and it's just, oh, by the way, that's that's less than this I've underlined in red. That's true. I don't actually use this. Your book tends to build arguments off applying the triangular inequality to that term and then doing stuff, but I don't know. I just prefer to work from the line I'm about to underline in green. So this is actually my logic flows along this line here. Again, I haven't explained what M is yet. So like this stuff down here told me to put M up there, right? So this is indicated by work down there, all right? Okay, so absolute value of x minus x not less than 1 gives me minus 1 and 1 above and below and above x minus x naught. Then I added x naught, then I added another x naught, then I added a b, and I finally got to this, right? Of course, this could be shortened. I mean, this is scratch work, right? So you can't judge me. Anyway, so I found that 2x naught minus 1 plus b and 2x naught plus b plus 1 are above and below, or I should say, yeah, above and below that quantity. And so if I let m be the max of the absolute value of this and that, then certainly if I have absolute value of x minus x not less than 1, then that implies that this quantity right here, right, this quantity right here is, less than m. All right, so I'm going to choose delta to be the minimum of 1 and epsilon over m because I know that that's going to then get back to here and be what I want. All right, so here's the proof. Proof. So again, the proof should be self-contained. Here it is. And my proof does have a gap, but I hope you can forgive me. Let epsilon be greater than 0, and let m be the max of absolute value of 2x naught plus b minus 1 and 2x naught plus b plus 1. The gap in my argument here is that it's conceivable that m could be 0. I don't think it actually can be. I think if m is equal to 0, then that forces like 0 equal to 1 here or something. But I haven't dug into it. I mean, there's something more to say there. All right, I'm going to just suppose that m is greater than 0 and leave the rest of the logic there to the reader. All right, my bad, but I'm going to go on. So let delta be the minimum of 1 and epsilon over m. Then if I suppose x minus x naught's less than delta, and well, that unpacks to give me minus 1 less than x minus x naught less than 1 because delta is less than or equal to 1, which then through the straightforward inequality work gives me 2x naught plus b minus 1 is less than x plus x naught plus b less than 2x naught plus b plus 1, right? But by the construction of m, I get that the absolute value of x plus x naught plus b is less than m. So consider then that the absolute value of f of x minus f of x naught is this minus that, but then algebra simplifies to this. C's cancel, right? And then factor out x minus x naught. And then by properties of inequality, this is the product of the absolute values, which is less than delta m. And remember that delta is less than or equal to epsilon over m. So the m's cancel, we got epsilon, and there we have it. F of x is continuous at x naught, and in fact, as x naught was arbitrary, we've shown that f is continuous on the reals. So there you go. There's an example for you, not in the notes. I mean, not in the textbook. And I hope it helps you. I might on the test or something. Maybe I would give you a similar example, but I'd actually put numbers in for B and C. I thought it'd be fun to do it with B and C arbitrary. So the example given in the textbook, the first example they give is, f of x linear, 3x plus 7. And that one's pretty simple. You can just pick epsilon greater than 0, choose delta equal to epsilon over 3, and it pretty well just works out. The 7's cancel. You get 3 times x minus x naught, which is less than 3 delta, which is, right, equal to epsilon in this case. So pretty easy. And since x naught was arbitrary, you've actually shown that f is continuous on the reals in example 3.3.1. All right, so note. The definition of continuity does not mention limits. This allows to include in the definition point x naught in D, which are not limit points of D. So in particular, if x naught is an isolated point of D, then there's a delta such that the if D looks, basically here's a picture, if D looks like this, right, it's got some continuous parts, right? Maybe the endpoints are closed, or they're included or not included, whatever. So what I've drawn all limit points, right? But then there's also like boop, 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 boop. These would be isolated points, right? Because there exists like, a little open ball around that one, such that the intersection of the open ball and the set of, the points in D, which I've illustrated by the black dots, D intersect with that green is just the point around which I'm illustrating there, x naught. So this x naught, this x1, this x2, those would be isolated points, all right? Because there exists an open ball around those points inside which there's not infinitely many points. Well, more to the point, there exists an open ball around the point in which there's just that point in the open ball, all right? That's an isolated point. Now, the limit point, remember, required that every open ball around the point contains infinitely many points in the domain in question, in the set in question. That's a limit point of D. And so, even on the endpoints here, right, it doesn't matter what open ball I take around that endpoint. There's infinitely many points, right? And this open endpoint, again, there's infinitely many points inside the set D, which are in the open ball, right? So those are limit points, and we've defined limits at limit points. Now, there's a couple different ways around this. Like, you could just sort of by fiat extend the concept of limit to isolated points, just to be able to write a formula for continuity. In some sense, that's what's done in calculus. Like, if you read a calculus textbook, right? Typically, depends on how careful the book is, right? But I'm certainly guilty of this. I've said that a function is continuous, f continuous at x naught, implies really if and only if, right? The limit as x goes to x naught of f of x is equal to f of x naught. I mean, that's pretty typical calculus 1, definition of limit, right? I mean, definition of continuity. And, well, that's not wrong if x naught's a limit point. See, but if x naught's an isolated point, then we can't talk about the limit, technically, as it's been defined in this text, all right? So what do? Well, using this epsilon delta definition of continuity, it goes back, if x naught is a limit point, right, then notice that this implies that the limit exists, because you can, if it's true for this, it's also true if you throw out 0, right? If you weaken the condition to not allow x equal to x naught, then you still get the implication. So like, this data for a limit point implies that the limit as x goes to x naught of f of x is equal to f of x naught. In contrary, at an isolated point, right? Well, that means there exists a delta so that, an isolated point, right? Let x naught be isolated for a second. Then there exists delta greater than 0 such that, b of x naught semicolon delta intersect with the domain in question D is just the singleton, right? And so if you pick a delta greater than 0 such that x is in D, and then this condition line right here reduces to, what does it say? So x in D, and absolute value of x minus x naught less than delta implies actually that, well, it implies x is equal to x naught, right? And that, of course, implies that the absolute value of f of x naught minus f of x naught is equal to 0, which of course is less than epsilon. So essentially, it is automatically true that a function is continuous at an isolated point. That's a side effect of this definition. Functions are automatically continuous at isolated points. So if you had a function whose domain was such that every point was isolated, for example, a function with a discrete domain, like a sequence, then in this definition, sequences are continuous with respect to our notion of continuity. And so there you go. It's not. I mean, it's not a bad thing. It's just that's what happens. All right. Of course, we're kind of getting on the edges of what we sort of intuitively want continuity to mean in terms of gluing points together, right? But all right. So, as he says here, therefore every function is continuous at an isolated point of its domain. Great. Here's a theorem, which I think I just basically explained. Let f be a function, x naught a limit point of d, then f is continued at x naught if and only if the limit as x goes to x naught of f of x is equal to f of x naught. Again, as I mentioned, this is essentially the typical calculus 1 definition of continuity, right? And so necessarily calculus 1 usually forbids discussion of isolated points, is what it boils down to. So in that context, this isn't a theorem. It could become a definition, right? All right. Anyway, so now they're showing the limit that this quadratic function is continuous by applying limit laws from the previous section, and that's fine, right? Perfectly reasonable way to be, but I thought it would be useful for you to see a proof from the epsilon delta definition. So I guess it's important for me on your next test to say, show this function's continuous from the epsilon delta definition. That would mean for you to give me an argument like I just gave you at the start of this lecture, right? Whereas if I just say prove that this function's continuous, then, well, you're free to use limit laws like this, right? All right. Another theorem, let f be, what do I see here? F from d to the reals, x naught a point in d, f is continuous at x naught if and only if for every sequence xk and d that converges to x naught, the sequence f of xk converges to f of x naught, right? So we can also characterize continuity by this corresponding sequential convergence, because remember, the continuous limit can be exchanged for the sequential limit by our previous work in the other section. And of course, then the limit laws transfer over to statements about the continuity of new functions built from old. In particular, if you have functions f and g and x naught a point in their domain, and f and g are continuous at x naught, then the sum and the product are continuous at x naught. The scalar multiple of f by a constant is continuous, and the quotient of f over g is likewise continuous at x naught, provided, of course, that the g of x naught is actually not equal to 0, right? Which is to say that f over g is actually defined. All right, so great. And I think the proofs of those are pretty obvious applications of the limit law, so I'll skip over them. He gives you proof of the sum one right here. So basically he's just saying, okay, so the limit of the sum is the sum of the limits, and since the limit is the function evaluated at the point, then by definition of f plus g, that's f plus g of x naught by the pointwise definition of sum of two functions. So, but this, actually makes a perfectly good test question right here, right? Like, prove f plus g is continuous. Like, it's not a bad question. Like this, anyway, it's not a bad question. And finally, the last theorem in this section, let f from d to r and g from e to r with f of d a subset of e, f is continuous at x naught and g is continuous at f of x naught, then the composite of g with f is continuous at x naught. And I think he just says, basically, well, they don't give proof, right? They just kind of go to exercises past then, but I thought it would be useful Unless I'm missing a page in my printout. I don't think I am, though. This is page 75, and this is page 76. But I think this is a good thing to see the proof of. I'm not entirely sure why they skipped it, but whatever. To each his own, I suppose. And anyway, here's the proof. Composition law for limits. So if you have a function, so here's just the theorem again. All right. So suppose f is continuous at x naught and g is continuous at f of x naught. Let epsilon be greater than 0. First of all, we can choose delta g greater than 0, for which the absolute value of u minus f of x naught is less than delta g for u in e. All right, because why? As my little brother used to say, cuz be why. So g of u minus g of f of x naught less than epsilon. Well, I can get this implication for appropriate u because we know that we have continuity of g at f of x naught, right? Okay, so that's piece of evidence number 1. Likewise, by continuity of f at x naught, we can select a delta greater than 0, such that if x is in D, I keep forgetting to say that, if x is in D and x minus x naught is less than x minus x naught is less than delta, that implies that the absolute value of f of x minus f of x naught is less than delta g. I can do that by the continuity of f, right, at x naught. So if I pick x in D with x minus x naught less than that delta, we find that the absolute value of f of x minus f of x naught is less than delta g, right? But then notice that f of D is a subset of E, which means that this f of x is actually an element of E. So we've got f of x is an element of E, and it meets the condition that element of E minus f of x naught is less than delta g, right? So thinking of u equal to f of x in the above, we find that g of f of x is minus g of f of x naught is less than epsilon. Consequently, in summary, for x minus x naught less than delta and x in D, we have the composite of g with f of x minus the composite of g with f of x naught is less than epsilon. That is, that g composed with f is continuous at x naught. So that's actually a very powerful way to prove continuity of a vast swath of examples is composition. The importance of composition cannot be overstated in terms of practical applications and seeing formulas for what they are. I would make the following comment, though. So, f continuous at limit point x naught means this limit of f of x as x approaches x naught is f of x naught. G continuous at the limit point f of x naught says that limit of u as u approaches f of x naught of g of u is g of f of x naught. And combining these, we actually have the rule, the limit as x approaches x naught of g of f of x is equal to g of the limit of f of x naught, f of x. Let's see here if I could say that other way. Yeah, so, and, I like to think of this, which is, essentially the wisdom of this theorem we just proved, as I tell calculus students usually that the way I think about this theorem is that for a continuous function, you can bring the limit inside the function, right? So like continuous functions allow you to bring limits outside in like that. And so anyway, that's that for this. The next section is, of course, a more deep section, and hopefully I'll get to that later today. So thanks, guys.